Stache, who was an alum, went through our program a few years back and major in chemistry. She had BS in chemistry. While she was here, she won a few awards, the ACS Division of Analytical Chem undergrad award, also our local ACS chapter Outstanding Graduating Student in Chemistry Award, which was decided upon by the entire department. After leaving Green Bay, she got her master's and PhD from Colorado State, spent some time as a postdoc at Cornell. Spent a few years getting experience in industry, and now she is an assistant professor at Cornell, and she's been there since 2020. And I think from there, I'll turn it over to you. Right, welcome.
Thank you, Mike, so much for that introduction. It's very exciting to be back here. I think the last time I was on campus was about 10 years ago. Things have changed a lot. But yeah, it's so special to be back here today. Thank you so much for the invitation here and accommodating my schedule and allowing me to be here today. I'm really excited to tell you all about what we've been doing in my lab for the last 2.5 years. We started in pandemic of 2020, but we've persevered. And we're very much focused on sustainable polymer chemistry. So there's a few of you here in the audience. How many people know what a polymer is? Just show of hands. Okay. All right, so a few of you know what a polymer is. For those of you online, I'm sorry you can't see my props, but I just selected a few from the catering that we have here. One is a coffee cup lid. It has the number 6 on it. That's polystyrene. So that is a plastic. It is a polymeric material. And there's another little clear plastic cup here. This is PET, or polyethylene terephthalate. That has a resin identification code of number 1. And so when you see those little recycling triangles on your plastics or those are polymers, and that's what I'm going to be telling you about today. So polymers have completely revolutionized our daily lives over the past 100 years. We've been making synthetic polymers for 100 years. You can't go 2 seconds without touching something that's a plastic containing a polymer. But with that, this has created a huge problem. So a study done by the Ellen MacArthur Foundation just a few years ago tracked what happens to polymeric materials as they're generated every year. And so we generate over 80 million metric tons of plastics in a year. So it's going to be your coffee cup lids, it's going to be detergent bottles, plastic water bottles, all of these things. And what you'll see on this somewhat scary graph is that 32% of those materials, 32% of 78 million metric tons ends up in the environment. And so this is being consumed by our wildlife. It's building up on the side of our roads. It's getting into the ocean. 40% of that ends up in landfills. And so it's somewhat contained, but it sits there somewhat indefinitely. So that's 70% of 80 million metric tons a year are ending up in the environment. Some of those materials are being collected and incinerated for energy. And so you can imagine burning those polymers or those plastics and turning them into CO2 and recovering the energy from that process. 14% of those are actually collected. And so when you throw your material into that blue recycling bin, those materials are being collected for recycling. So only 14%. A lot of those are lost. 8% of those are turned into downcycled plastics, meaning they don't have the same function as the virgin materials that were made. And then 2%, just 2% of the plastics we produce every year are actually recycled into a high value material. So we're producing plastics at an exorbitant rate, and we're not doing anything with them afterwards. They're ending up in the environment. And so what this means is as these plastics build up, they start to build up in the oceans. And so we now have essentially plastic islands in the Pacific Ocean. And this is, again, going to affect our ecosystems. It's also projected that by 2050, we will have doubled the amount of plastic waste that currently is in the environment. And so it's, I think the metric that people like to say is that the plastic in the ocean will outweigh the fish. And so that's somewhat depressing and very, very concerning. And just to give you a scope of what this looks like, just to give you a visual for how much polymeric material this is. You think about the water bottles that are produced per day, about 1.3 billion bottles. Compare this to the Eiffel Tower. This mountain is about half the height of the Eiffel Tower. So that's all the plastic, and that's just plastic water bottles. Produced in 10 years, 4 trillion bottles. This blue mountain here is overlooking Manhattan. So that's a lot of plastic. That's a lot of volume. And all of that is building up in our environment. And yet we're only recycling to high value materials 2%. And so how do we think about this? Polymers are generally coming from oil feedstocks. so petroleum. We refine these into monomers, which are the repeat units that are going to build up into these plastic materials. We make the polymers, we formulate them into the products, we can shape them depending on their polymer properties and the applications we want to use them for, and then unfortunately, they end up largely in the trash. For the polymers that are recovered, the plastics that do end up in the recycling bin and get recycled, they generally go through a process called mechanical recycling. And so what this means is that they bring the material into the recycling center, they have to separate it based on the type of plastic, which means these two materials, which are very different polymers, can't be mixed together. Even something as similar as polyethylene and polypropylene, which are very structurally similar, will not mix together. And so those have to be separated to make a high value material. So they chop them up into little bits and then they can reformulate them into a new product. And so that's the 2% that is actually recycled into high value materials. And so the challenges with mechanical recycling we currently have are separating the different types of plastics. How do you actually separate these two different materials, which functionally look identical to the average person? And even if you can do this mechanical recycling process, this is still going to erode the properties after a few cycles. So mechanical recycling is really not a long-term solution, although it does recycle 2% of our materials. What we really want to do is something called chemical recycling. And this is turning the polymer, the product, back into its constituent monomers. So those repeat units that we've developed all of these synthetic techniques to make, so we can reformulate these into virgin materials, which will have the properties of the polymer that we want. So the strategies here are, again, how do we separate these different types of plastics? And how do we develop a strategy for chemical recycling, which is basically running the reverse of a polymerization backwards to get monomer so we can repolymerize it. And developing that strategy, which is going to be compatible with waste streams, right? If you throw away your plastic material, it's generally not cleaned ahead of time. So there's going to be dirt and oxygen and all these different things that we have to worry about. And so these are really the questions that we're interested in solving in my research group. We're developing new strategies, new polymerization strategies for making degradable polymers. So even if they end up in the environment, they can break down over time. We're also developing selective upcycling methods. So we can take something like this polystyrene lid and turn it into a different commodity chemical, which can be valuable for some other industry, rather than having them end up in the environment. And thirdly, which I'll talk about at the end, we're developing chemical recycling strategies to convert these polymers back into their monomers so they can be repurposed in a polymerization or some other application to make virgin materials. So we have a completely closed loop cyclic system, so we're not really generating any waste. And so our first strategy is thinking about how to render commercial polymers photodegradable or biodegradable so that they can break down in the environment. And so if we look at many of our commercial materials, so polypropylene, polyethylene, these are the two most mass-produced polymers that we have. PVC and polystyrene are other commodity commercial polymers that we use. These don't break down in the environment. They leach out into the environment and they will sit there for hundreds of years because they are so stable and inert to environmental conditions. However, if we introduce some sort of oxygen or functionality into the polymer backbone, it can be photodegradable. So these ketones here can absorb visible light and then they can start to fragment and break down in the environment. And so we question how we can install this ketone functionality into these commercial polymers. How can we develop methods to make these polymers photodegradable? And so different strategies that people have used over the past 50 or 100 years are copolymerizations of commodity monomers. And so this is ethylene monomer. This is carbon monoxide. These are used in polymerizations industrially. And so in this case, Mecking showed that you could perform a radical copolymerization of these two monomers to make essentially polyethylene with ketones in the backbone. So if this polymer leaches out into the environment, it can break down over time. And so when we irradiate it with visible or UV lights, it will break down into smaller pieces of polymer. And so this is a great strategy for making these polymers photodegradable. It uses commodity monomers. It provides non-alternating, meaning there's only a small percentage of these ketones in the backbone, which means it doesn't change the physical properties from the polyethylene that we know and love and use every day. The challenge is it only works for ethylene. So ethylene is the only monomer that this strategy will work with. And the reason being, not to get into too many technical details, but in a radical copolymerization, If this reacts with carbon monoxide, it will generate an acyl radical, which can undergo a reverse reaction. So this is in an equilibrium. And so we need a high pressure of CO to drive this forward so that we can put this ketone into the backbone. So this is great for ethylene, and we can drive this process forward. But in the case of any other alkene monomer, other than ethylene, so any substituent on here, we can't drive this process forward because the reverse reaction lies to the activated stabilized radical. And so this acyl radical will rapidly decarbonylate, and so we can't incorporate CO into the backbone of these polymers. And so we looked at this problem and we thought, okay, we can't use CO to install these ketones. So instead, we're going to use a different C1 component rather than carbon monoxide that isn't going to go that reverse reaction. So we can drive the polymerization forward and install those carbonyls. And so what we decided to do is use isocyanides, which are isoelectronic to CO, meaning functionally they're very similar, they react the same, but they don't react the same in every facet, meaning they don't undergo that reverse decarbonylation reaction. And so in that way, we can generate this polyisocyanide, which is functionally very similar to the polyketone, and we can remove this group by just treating with acid and a little bit of water, with a little bit of acid and water, to reveal the polyketone that we want. And so we can generate these polymers by using this other type of monomer. No, don't freeze on me. And my computer froze. There we go. Okay. So my student, Layla, is a third-year graduate student. She took methyl acrylate, which is a common monomer, polymerized it with this bench-stable isocyanide in a certain monomer ratio. And with AIBN, which is a very common radical initiator, she was able to see incorporation of that isocyanide in a non-alternating fashion. And we could tune this depending on how much of the isocyanide we use, with, however, uncontrolled molecular weight and broad dispersity. And I'll talk about what that means in just a second. So this uncontrolled radical polymerization does not give us predictable molecular weight. And so that means we can't necessarily predict what the properties will be ahead of time. And so we needed to find a different strategy to do this. And so free radical polymerizations, generally we take a thermal initiator like AIBN, which you may have used in lab. And in the presence of monomers, we add some heat, and this will grow polymer chains. And so all of these little pink balls will start adding together and we'll get long polymer chains. But we don't get uniform growth. And so the molecular weight, or the MN, will increase very quickly, but not consistently with the monomer as it's being consumed. And so what this means is that we don't have control of molecular weight. These chains are all different sorts of lengths, which is going to change their polymer properties. And so this method doesn't give us a lot of control over the polymer at the end of synthesis. So instead, what we've done for the last 30 years are develop controlled polymerization strategies, where we can use some sort of reversible deactivator so we can keep our radicals, which are highly reactive, at a low concentration. And now we can get uniform chain growth. So all of these polymer chains are now the same length. Molecular weight increases linearly with conversion. And so as we consume the monomer, we grow the polymer chains at a uniform rate. And now we can do things like copolymerizations, we can control the architecture, and overall the molecular weight distribution, which is the uniformity of these polymer chains. And so in order to conduct this polymerization, we need to use a strategy of controlled radical polymerizations. And we turn to cobalt, which is a transition metal, which can reversibly deactivate propagating radicals. So typically the way this is done is we take AIBN and methyl acrylate monomer, we heat this up, it starts generating these radicals shown here. These will couple with a cobalt-2, so these two join together, and you get a dormant species, which doesn't do anything. So this species right here is inert, and then once we reach enough of this, this will enter into an equilibrium where the chains can continue to grow and propagate and become longer. So Layla tried this chemistry, now adding a cobalt complex, and again, using AIBN, same feed ratio. She sees similar levels of incorporation, but now we get a really small polymer, and we still don't have good control over the dispersity. We're targeting levels of 1.1 or 1.2. We're seeing broad dispersity and low molecular weight. And so the challenge here is that we have a very long induction period. That means there's no polymer growing, but we have radicals which are starting to be generated. And so we first need to generate a high enough radical concentration that we push the equilibrium over to this dormant species. So then we get into the polymerization through this reversible deactivation equilibrium. And so right now we have too long of an induction period so that side reactions can occur with our isocyanide. And so we needed to develop a new strategy for initiating these types of cobalt-mediated radical polymerizations. And so my postdoc, Sajad, developed an instantaneous initiation method where we don't have to wait for those radicals to be generated over time, and we don't have to worry about those side reactions. And so what he did is he took cobalt-2, he oxidized it, and then treated with a silane to generate a cobalt-3 hydride, which can rapidly add across the alkene, and then we generate the same species that we saw before, except we do it instantaneously. So now we can run the polymerization. And so using this cobalt complex, methyl acrylates, this oxidant and silane, which aren't really too important, he now gets a very well-controlled polymerization. So the molecular weight that we programmed in is exactly what we see. And the dispersities now are less than 1.1. So this shows us that the chains are very uniform in length, and we have control over the polymerization. Now there's a lot more interesting mechanistic nuance to this, but I really want to focus on sustainable polymer chemistry now. So I'm going to show how we use this then in copolymerizing isocyanides with methyl acrylate. So this is Layla, I didn't show her picture before, but now using this protocol that Sajad developed, she observed a very well-controlled polymerization. So now we have predictable molecular weight. We programmed in for 8.6, and that's what we see. And now we have low dispersities as well, so 1.2, with, again, controlled incorporation, 3%. And so we wanted to see if we could change the amount of isocyanide that's being incorporated into the polymer by changing the feed ratio of these two monomers, so methyl acrylate and isocyanide. And so she changed from a 9:1 feed ratio all the way to favoring isocyanide, so having that one in huge excess. And what she sees is an increasing, almost linearly increasing amount of isocyanide being incorporated into the backbone of the polymer, which was very exciting. So now we can tune how much of this degradable functionality we have in the backbone just by changing that feed ratio. And so she was able to show then that once we have this polyisocyanide, we can treat this with an acid and a little bit of heat, and we can generate the polyketone, which is what we wanted to access in the first place. But now no one has ever actually accessed, laser pointer just died. No one has ever actually accessed this type of polyketone structure before. And so we're currently studying the degradation profile of this. I can't go into any more details because we have some IP or patents pending on this, but we're very excited about where we can take this work and show that we can make commercial polymers now degradable. And there's a lot of opportunities here to make really interesting materials. So that's our story on developing new polymerization methods for making degradable polymers. Now I want to move into our selective upcycling methods. And so this is taking commercial products and instead of throwing them in the trash, finding a different fate for them. And so instead of throwing them in the trash, what we want to do is turn them into some other type of useful chemical, perhaps like a fragrance or a food additive or something like that, some other sort of commodity chemical. And so our challenge here is activating the polymer backbones so that we can get selective product formation. And so we look at a lot of our different commercial commodity polymers, polyethylene, polystyrene, PVC, polyvinyl ethers. They all have a lot of hydrogen in the backbone. So these are carbon-hydrogen bonds. And if we can activate these carbon-hydrogen bonds, then we can activate a site on the backbone of the polymer. And so we're going to use our understanding of organic reactivity to start breaking open these polymer backbones, which are typically inert under environmental conditions. And so there are other groups that have worked on this chemistry that have upcycled polyolefins like polyethylene using CH abstraction to get functionalized, which have now new material properties. What people have looked at for a long time is photooxidative polymer degradation. So I mentioned at the beginning that polymers don't break down very quickly in the environment, but when they do, it's through this photooxidative mechanism. And so they absorb UV light, they react with oxygen, and then they can start to oxidatively cleave the backbone and fragment into smaller pieces. But no one's ever studied what they fragment into or tried to control how they fragment. And so we looked at polystyrene. Polystyrene is not recycled in any meaningful amount, and it consumes 1/3 of the world's landfills by volume. And that's because a lot of what polystyrene is polystyrene foam, styrofoam, right? So that takes up a lot of space. Okay. And so polystyrene is worth $45 billion a year. That's just the foam market. That's not high impact polystyrene or other polystyrene products. So just styrofoam essentially. or expanded polystyrene foam. But the waste product is worth essentially nothing, $157 million in comparison to the $45 billion that we make every year. And that's decreasing over time. And this is through economic restrictions, states outlawing use of polystyrene. Essentially, polystyrene waste is worthless. And so no one wants to buy it, and it just ends up in landfills and in the environment. And so we have to find new function for this material, an economic benefit for recycling it so that it doesn't build up in the environment. And so if we look, we have this aromatic ring, and we're thinking about how we can turn that into a product of value. And so benzoic acid here on the right and benzaldehyde are worth almost $1.5 billion per year. Acetophenone adds a little bit more value, again, an aromatic ring with a little bit of oxidation. Phenol is worth $22 billion a year. And so if we can convert polystyrene into phenol, that opens up a huge revenue stream for this waste product. And then benzene is worth even more than the polystyrene market. And so if we can think about ways to convert polystyrene into these products, we can now give it value, which will promote people to actually, will encourage people to actually want to recycle and further develop these commercial methods. And so we needed to find a strategy to activate the backbone of the polymer controllably, reproducibly, but also inexpensively. Right? You think about the polystyrene market, the waste product itself is worth nothing. And so we have to find value from it. We also have to do it very cheaply. And so we turn to base metals like iron, which are very abundant in Earth's crust. If we take this iron trichloride compound, irradiate with light, it can abstract a hydrogen atom and in the presence of oxygen, oxidize something like cyclohexane. And so what we proposed or what we imagined is that we could take iron trichloride, generate chlorine radical, which will abstract a hydrogen atom very efficiently, generate these radicals on the backbone of polystyrene, and then in the presence of oxygen, it will react with oxygen and then start to oxidatively cleave into these small molecule byproducts. So this is work done by a graduate student, Sewon. He took a lab synthesized sample of polystyrene. So 86 kilodaltons is essentially what the size of this polymer is. He exposed it to iron trichloride in the presence of oxygen, visible light, and in acetone, which is a very cheap solvent, and then detected all of these different oxidized aromatic products in a GC chromatogram, and then also observed this oxidized polystyrene or styrene oligomers. And so of these first three of benzoic acid, benzaldehyde, benzoyl chloride, he detected 37 mole%, which means that every 37% of these different repeat units were converted into this product. So 37% of the polystyrene, most of it being benzoic acid, and then a small amount of acetophenone, and the remainder of the sample being these oxidized styrene oligomers. I hope that didn't turn off. Okay. And just looking at the product distribution as a function of time, how long does this process take? We tracked it for about 2 days, irradiating the sample, and we see that benzoic acid continues to grow in over time. If we let this go for longer, so up to 5 days, we can convert 50% of these styrene monomers into benzoic acid. This doesn't just work on lab synthesized samples. We also use some of these. So I drink a lot of coffee. And so I have a lot of these lids sitting around. And so I give them to Sewon and he takes them into the lab and he starts to break them down. We also had this clear lid for a cake and another coffee cup lid with some black dye. And in the case of the clear lid or styrofoam, we see that our process works very well. We can still convert this into benzoic acid. But one of the challenges we face in plastics recycling is that a lot of the materials we make are not pure polymer. They're not pure plastic. They have dyes, they have composite material, they're mixed polymers. And so this is what we see here in this coffee cup lid that we have. There's white dye in there, there's composite material that doesn't break down. And in the case of this black coffee cup lid, which I'm pretty sure is entirely cosmetic, that black dye inhibits light penetration into the system. And so now we can't break it down for that reason. So we have to find a way to remove that dye to improve our process. So this is just to illustrate the challenges that we face in plastics recycling. But the good news is that we can also scale this process up. So in these examples up here, we're doing this on a very small scale, but we can use a photo flow process, which means essentially we have a long tube and the light is shining on it. And so we get really good surface area, really good light penetration. And so in that way, we can scale up the polystyrene degradation. This is just a gram, but we can now do this in less than a day. right? Instead of taking the 2 to 5 days that we had in batch, we can do this much more quickly. And we're working with another company to further optimize this process. We can show that we can do this on kilograms and then hopefully metric tons, which is the scale of polystyrene waste. The mechanism is shown here very briefly. I'm just going to go through this really quickly. It's a little bit technical, but basically we abstract hydrogen atoms, it reacts with oxygen, starts to cleave the backbone, generates benzaldehyde, and then that gets oxidized to benzoic acid. And there's a few different pathways I can go on here, but I'm just going to skip over those for now. We also propose that this is one of the CH bonds we abstracted, but the other one we can also abstract to get benzoic acid. This is not restricted to just polystyrene. We can also use this on other commercial polymers. And so Darren is an undergraduate in my lab. He's a third-year undergraduate. And so he's working on vinyl ether degradation, which is shown here as this repeat unit. So polyvinyl ethers are commonly used in adhesives. And so if you have your little Post-it notes, there's probably some polyvinyl ethers in those, lubricants, anti-corrosion agents, things like that. And in this case, he subjected this to similar conditions that Sewan was using for polystyrene degradation. And we can activate the backbone using chlorine radical, which we can get chain cleavage, or we can activate the side chain, and then we can get cleavage of the side chain to get these oxidized small molecules. And so there's 2 different pathways we can go through. And so what he found, he tracked down these different molecules, again, using GC, and found about 30 mole% total of small molecules. So 30% of these repeat units were being converted. And interestingly, what he saw is that at earlier time points, we actually have a much higher yield of the products. And so we have 30% of this alcohol shown here at 2 hours, but it starts to decompose over time and turn into this carboxylic acid. And so what this shows is that we need to think about how these CH bonds are being abstracted and how products are being generated over time, and continue to develop our process to get selective and high yielding degradation of these polymers. But very promising start to converting isobutyl or vinyl ethers into useful commodity chemicals. And so when we published this work on polystyrene photooxidative degradation, a bunch of other people published papers at the same time. So this area has gotten very popular. A lot of people are looking into polymer recycling. And so a number of different strategies were used, using iron trichloride, using benzophenanes, singlet oxygen, anthraquinones, NBS. And in all these cases, the bond dissociation energies are greater than 100 kcals per mole. And what that means is that we don't get any selectivity. That's a very high number. And so that can abstract any of the CH bonds in polystyrene. And so, right, there's a possibility of abstracting this tertiary CH bond, which has a bond dissociation energy of 88 kcals per mole, which is much less than 100. So we can easily use any of these reagents to abstract that one. But similarly, the secondary CH bond is also less than 100 kcals per mole, and so we can easily abstract that one. And so we don't get any selectivity between those 2 CH bonds. And so this is really where we're taking this chemistry is, can we get selective H atom abstraction so that we can change our product distribution so we can access some of those other commodity chemicals, which also have even more value than benzoic acid. So for example, can we abstract this secondary CH bond and drive this to higher yields of benzoic acid? Or can we change the conditions such that it doesn't get oxidized, benzaldehyde doesn't get oxidized, and we can isolate that product? If we abstract the tertiary CH bond, we can turn this into acetophenone instead of benzoic acid. So now we've changed that product distribution to favor a new product. And changing the reaction conditions, can we now get benzene instead of either of these oxidized small molecules, which has a huge market value? And so using our intuition and our understanding of organic chemistry, we're going to develop these reagents, these inexpensive reagents that can convert these commodity commercial polymers into products of really high value. And so we have a lot of really cool stuff going on here. Again, it's all being patented at this point, so I can't talk about it, but stay tuned. Okay, so the last story I want to tell, which is good, we're good on time, is chemical recycling. So turning polymer products back into their monomers so we can repurpose them and make virgin materials. And so this is what we call a cyclic plastics economy. We have a polymeric material that can be depolymerized over the lifetime, depolymerized back in its constituent monomers, and then we know how to polymerize those into the polymers that we use every day. And so what are the challenges with this? Why aren't we using this chemistry right now? One of them is overcoming the stability of the polymers that we are producing every year. So the kinetic and thermodynamic stability of these polymeric materials. So again, you've seen these before: polyethylene, polystyrene. I'll add two new ones here: polymethyl methacrylate, this is plexiglass, and polylactic acid, which is also found in water bottles and coffee cups. So these polymers are incredibly inert to environmental conditions. In order to thermally break down these polymers, you have to heat them up to very high temperatures. That's the kinetic stability of polymers. They exist in the environment until you raise them up to this temperature. As you can see down here, these temperatures, these are very large numbers, right? That's a lot of energy to raise those polymers up to those temperatures. The second challenge is that the reason we can make polymers so easily and so cheaply is that they're driven by enthalpy, forming these new carbon-carbon bonds. This is a thermodynamic driving force. And so driving that process in reverse to get the monomers back is very energetically uphill. So again, we need to pump in a ton of energy in order to drive that process. Again, very large numbers, taking a lot of thermal energy. The second challenge is developing a highly selective process to make monomer. We can take polymers and we can start to break them down. In our photooxidative work, we're primarily generating benzoic acid, which is good. But if we don't generate one product, then we have to think about separations. How do we separate all of these different chemicals on a large scale? So we need to get high selectivity for the monomers, so then we can just reuse them to make new polymer. The third challenge is a lot of economically driven. How can we do this with ambient conditions that are be compatible with our waste streams? And the fourth challenge is, how do we get selectivity for a single polymer to break down in a mixture of polymeric materials in a mixed polymer waste stream? And so we looked at this problem and we thought, well, heating it is a really good strategy for breaking down these polymers, right? If you pump in enough energy, you're going to break them down and you can get these challenging bond activations. And we'll worry about these other issues over here. And so just thinking about bulk thermolysis of carbon-carbon bonds, if we look at this CC bond here, which is from polyalpha methylstyrene, has a high activation barrier. And so you need to pump in a lot of thermal energy to break or homolyze that carbon-carbon bond. And so if you heat this up to 60 degrees, it'll take 343 years to break half of those carbon-carbon bonds. Obviously, that's not going to work. However, if you heat it up to 290 degrees C, now you can break those down in just a few seconds. And then if you start generating those radicals, then it can depropagate and form monomer back. And so we have our polymer, we heat it up to 290, we generate this high radical concentration because it only has a half-life of 2 seconds, so you're going to break a lot of those carbon-carbon bonds, but in doing so, you can generate monomer. You're also going to have side reactions because you have so many radicals which are highly reactive. These can react with oxygen, they can react with themselves to reform that bond, or they can react with a different one, which will give you a new compound. So we can definitely generate monomer in this process. We're also going to get a lot of side reactions, which is not a selective monomer stream. Oops. Instead, if we can find a strategy to generate a low radical concentration, then we can pull off monomer and not have any of these side reactions and get a clean monomer stream. And so this is the question we asked. How can we controllably generate low concentrations of radical for selective reactions? And over the past 15 years in organic chemistry, we've done this using photocatalysis. So we use visible light to generate radicals with controlled concentration and temporal control. The light's on, you're generating radicals, turn the light off, it stops. So we can do this a few different ways. We can do direct excitation, where the molecule itself will absorb light and move into an excited state and do chemistry. We can do this with a second photocatalyst, or with a photocatalyst, which can absorb the light and then transfer that energy to a molecule. So like a single electron transfer process. Or it can undergo energy transfer, where it transfers that excited state energy to the small molecule and then generate an excited state species, which can go on and do chemistry. In all of these cases, we can do this very controllably by controlling the concentration of the photocatalyst or the substrate and the wavelength of visible light. So a process that we don't commonly use in synthesis in photocatalysis is internal conversion of these excited state photocatalysts. And so generally we hit these photocatalysts with light, they move into an excited state. If they don't do any chemistry, they will fluoresce or they will phosphoresce. They'll give off a photon of light. Generally what we don't want is for it to relax back down in a non-radiative fashion, in which case it gives off heat. if we can promote that process of internal conversion or vibrational relaxation, where it only relaxes back down, we can actually generate a lot of heat. And so there are a lot of materials, inorganic materials that will do this, plasmonic nanoparticles like gold and silver and copper oxide, carbon black, which is an oil petroleum feedstock and very cheap. And so what we sought to do is identify materials that will undergo this non-radiative decay to generate thermal gradients so that we can generate radicals. So comparing bulk thermolysis, where we heat up the entire solution to 290, so there's a very short half-life of these radicals, we get a high radical concentration, we get oxidized byproducts, or using this idea of temporal heating, where we have these nanoparticles which will absorb visible light, relax back down non-radiatively, and generate thermal gradients such that only the polymers or the carbon-carbon bonds that are in proximity to those nanoparticles will cleave and generate radicals. And so we can spatially and temporally control low radical concentrations so that we get selective depolymerization to monomer. So a few other groups that have been working on this, mostly in polymer degradation. And so they mix on small scale the polymer with nanoparticles, hit it with light, and they get oxidized byproducts or oligomers. A lot of these cases are using lasers. It's very small scale and using toxic or noble metals. And so instead we turn to carbon-based materials using standard LEDs, light bulbs, so that we could get near quantitative monomer recovery. This is work done by Liat, a fifth-year graduate student in my lab. She solution processed a polymer and our nanoparticles to make this film. This is polyalpha-methylstyrene. She hit it with light, and in just 30 minutes, she observed 66% conversion to the monomer. So the polymer is depolymerizing back into monomer, and then the leftover material is just oligomers of the polymer. You can kind of see, it's a little bit hard to see in this picture, but there's a little film right here sitting over the light. This is what it looks like before radiation. And then afterwards, you can see this condensation. This is the monomer. And then this little black piece is leftover nanomaterial and polymer. And so we wanted to compare our results of using this idea of photothermal heating to what would happen in bulk heating. And so under our system, we get 66% of the monomer, the leftover being recovered polymer, and less than 1% of this oxidized byproduct. And so we're not seeing those bimolecular side reactions to complicate our product stream. If we heat this up under similar conditions to 270 degrees C, so this is now bulk heating, we do see polymer depolymerization. So we get 13% of monomer in the same amount of time. So not as much. So we're not getting, we're actually getting hotter in the photothermal catalysis example. We still don't see any byproduct. If we heat this up another 10 degrees to 280, now we get comparable amounts of monomer formation, but now we're seeing this oxidized side product. And if we heat it up to 290, we actually see a decrease in monomer formation and more oxidized side product. And so what's happening is that with bulk heating, we're getting a higher concentration of radicals, and these are undergoing side reactions. It's in contrast to our method of photothermal catalysis, where we generate a very low concentration of radicals so it can selectively depolymerize back to monomer. I showed you a very tiny film, like 10 milligrams. Liat has been able to scale this up to 1 gram. She hasn't gone past that. We think it'll be pretty scalable. And in this case, she doesn't have to solution process the polymer. She just has the polymer, she adds the nanomaterial, she stirs it up, hits it with light, and you can see all this liquid here is now monomer. And so it depolymerizes actually an even higher yield as we scale this up to 73%, with the rest of it being the leftover polymer. And we can do this in a distillation type setup where the monomer comes over into a receiving flask in pure, analytically pure form. The NMR looks beautiful, very clean. This is not restricted to that one polymer that I just showed you. We can also do this for other polymers. And so cyclic polyethylaldehyde is commonly used as a photoresist. You can see the thermodynamic and kinetic parameters here. We don't need as much energy to start breaking this polymer down. And if we do break a bond, it'll start to depolymerize very quickly because it'll depolymerize at minus 36 degrees C, which is very cold. And if we use our protocol, albeit changing it to green light, we can depolymerize this to 78% of the monomer. And so this is a very different monomer than the alkene that we were generating in the other case. Comparison to the thermodynamic parameters, we have a much higher sealing temperature, and a much higher degradation temperature, and yet we can do this on small scale to 66% yields of this monomer. Moving on to commercial polymers, so plexiglass, PMMA. The kinetic barrier, so the degradation temperature, is similar to that of polyalpha-methylstyrene, But now the thermodynamics are really working against us. 220 degrees C to drive that process in reverse. And so in this case, we needed to actively pull off monomers. We did this under vacuum, but we can still get the polymer to depolymerize back to monomer in 64% yield. And then polylactic acid, which is an increasingly used biorenewable plastic. You're going to see it in all your water bottles, in your coffee cups, packaging materials, things like that. In this case, this polymer is very hard to depolymerize in the absence of a catalyst. You need very high temperatures, then it's going to be it will be very unselective for monomer formation. We can use a co-catalyst. We add in a little bit of a Lewis acid, zinc oxide. Under our photothermal conditions, we get 95% of the monomer back, with 90% of it being L-lactide, which is what we use to polymerize to PLA. So this process is highly selective for forming the monomer, even though these are all 4 completely distinct polymers. We can use a single strategy, or we can use co-catalysis to depolymerize these. And then lastly, just to show one of the huge advantages of using photothermal catalysis over thermal, just standard bulk thermolysis, is getting spatial control over depolymerization. And so if we take our polymer with the nanomaterial in the presence of plexiglass or polymethyl methacrylate, under our conditions of visible light, we only see formation of the polyalpha-methylstyrene monomer. This 1%, and I should really put this over here, actually came with the material. So there's a little bit of monomer in there. So that was not formed under our conditions. It came with the polymer. And we see less than 1% of acetophenol byproduct. However, if we heat this up to 290, now we get no selectivity for monomer formation. Both of those polymers are going to depolymerize, and we have to think about how we're going to separate those in a mixed product stream. And we start to see this oxidized byproduct. And so this really shows that our photothermal catalysis method can give us selective and hopefully eventually iterative depolymerization of commercial polymers into clean monomer products. Just to give you a little visual of what the data looks like, this is our polymer starting out. So this is an SEC chromatogram. This is polyalpha-methylstyrene with the nanomaterials. This is polymethyl methacrylate. You can see if we use visible light, this gives us, it doesn't change the polymethyl methacrylate at all. And we see this peak disappear because that polymer has been depolymerized. However, if we use this, if we heat it up to 290, now we see both of those peaks move over into this oligomer peak, and we have both of those monomers to deal with. And a nice visual, you can see here, this is what the film of the nanomaterials and the polymer, and this is polymethyl methacrylate. We use visible light, the polymethyl methacrylate is unchanged, it's all still sitting there. We can see the polyalpha-methylstyrene condense and the leftover oligomers. In bulk heating, both of them get depolymerized and mixed together. And so we can see the film here, polymethyl methacrylate. After heating, they're all gone. And they're just a mixture of different monomers and oligomers mixed together. So there's no selective depolymerization with bulk heating, but we can get selectivity using this idea of photothermal catalysis. So with that, told you about 3 different programs going on in our lab right now. Hopefully be really cool results coming out in the next couple of months, and hopefully those patents get filed so I can talk about it more. But lastly, I just want to thank my group. I work with an incredible group of students, a number of graduate students and undergrads. A recent picture we took at Cornell, and the leaves are all still on the trees. They're all gone now. Some collaborators who just got some federal funding from Cornell. If you want to check out our social media, we have a lot of social media to try and promote awareness about plastics recycling. And so we have a TikTok channel, Instagram, Twitter, and this is some sort of QR code which links you to all of those. Technology is not my thing. My students do it though. And thank you again so much for the invitation and for your attention. I'd be happy to take any questions. Yeah.
The acronyms that you're throwing out there, various polymers, they're kind of familiar, just kind of part of the jargon that gets thrown around, but I had never heard of PLA before.
Okay.
And then now this last year, I've been immersed in it because of a shop here on campus that's doing 3D printing.
Yep.
And once it sounds as though you were saying, the more we do with PLA, the better off we are in terms of recycling.
Yes. Yes, I would absolutely say that. PLA it's not one of the most mass-produced polymers yet, but it is easier to recycle. it's also biodegradable. And so if it gets out into the environment, either microorganisms or just acid and base in the environment will start to cleave those bonds and convert it back into something like lactic acid, which lactic acid is something that is found in our own bodies. And so it's not really, I mean, it can certainly change the microenvironments where it's generated, but in principle, it shouldn't be harmful. So PLA, I think, is definitely a polymer that people are increasingly using for the fact that it is more recyclable and biodegradable. We actually have a 3D printer in our lab as well.
There seems to be a local business that's betting a lot on manufacturing PLA feedstock for all the different brands of printers.
Yeah.
Thank you.
Yeah. If I can, oh, there's maybe a question in the chat. Oh, thank you. You're welcome. Yeah.
So when you do the reactions, you add that photocatalyst, shine light, breaks down the polymers, and then I assume you're going to have the photocatalyst back out at some point. Yeah, I was just wondering, is that a big challenge or is that a pretty easy thing to overcome? Or is that?
You're talking about the last program?
Yeah.
Yeah. So we haven't gone down that road yet. I can't share what the material is because it's proprietary. But one of the limitations of our method currently is that we think it is reacting a little bit with the polymer. And so it's going to be really hard to separate. And so right now we're not getting, you can see we're getting like 73% monomer. It's not going to 100%. So we have a different photothermal agent, which gets us to 90%. And that one we can easily separate. So I think, where we're going with this, we've illustrated the concept, and now we're going to further develop these materials so that we can more easily separate them at the end, or just get it to go to 100% so that all we have left is nanomaterial and monomer on one hand. But yeah, it's definitely one of the challenges. Madeline have a question? Nice. There it is.
I don't have a question, but a comment. If I were on the chemistry faculty at UW Greenville, I would be so proud of you.
Oh,
The stuff you're
thank
doing
you.
is amazing. I just, was looking down in the lower right hand corner of your slides. And there's all the publications, working at an Ivy League school.
Yeah.
My goodness, you have really done well. And, be really proud of you, and I'm proud of my chemistry colleagues for contributing to your education and the way that you've gone. So.
Thank you. Yeah, I mean, they definitely inspired me to go into organic chemistry and do research, and yeah, I'm definitely very thankful to everyone who influenced my education, and fantastic institution that got me started.
So my background is meteorology.
Okay.
And so I was just looking at all the temperatures. And so when you've got to get the temperatures up where they're at, and I have no idea what these labs look like. So how do you generate temperatures that are getting up, 200, 300, 600 C?
Yeah, I guess I'm not sure exactly what the reactors look like, but my guess is it's all fossil fuels to heat these things up. I mean, there are recycling, they're recycling or pyrolysis plants, which I think actually the industry is really digging in on using pyrolysis for chemical recycling that can heat these polymers up to that temperature and get semi-selective depolymerization back to monomer. I just think from, if we can't use biorenewable energy to facilitate that, I don't understand how that's going to be a long-term solution. Fossil fuels are going to run out at some point. And so that's why I think we're really excited about using visible light. So we have an experiment where we use sunlight to do this depolymerization. It's a focused sunlight, and there are definitely, mass units to focus sunlight, so you can actually think about using it on a large scale. And people are using that with photothermal conversion to purify water. actually. And so in third world countries, you can use these nanomaterials. You raise water up to a certain temperature, you kill or denature all of the proteins, and then you've purified it. And so people have been using that before. But I think, the fact that we can use something like sunlight to drive depolymerization is really exciting. I mean, there's certainly issues with scale, and we have to think about engineering that. But I think, if it works, we can definitely think about an economic reason and a societal reason, a moral reason to do it, right? So yeah, Kier, you have a question, recommendations for what we can do as consumers to help steer the movement towards sustainable use of plastics. I think we're already starting to see this in some states, like California has outlawed the use of plastic bags in grocery stores. New York has done the same thing. New York is also banning styrofoam or production of styrofoam. And so that's why styrofoam is really decreasing in value. And so I think, getting out and vote, like election day is coming up on Tuesday, right? Bring this up to your local politicians and, tell them that this is really important. I think right now there is no economic incentive for these companies to think about recycling. It is so much cheaper to just keep producing new plastic. It's dirt cheap. Recycling, especially something that's worthless, you have to find some sort of value in it. And so I think, if we can convert polystyrene into some of these products that have a lot of value, that's really exciting, and maybe that'll start to motivate people. But I think unless there are actually political and social pressures on these companies to think about recycling, it's not going to change. So we're doing our part by trying to develop the chemistry and get people excited about it, and give talks like this, right? So y'all are aware of some of the challenges we're facing, but I think, not buying certain plastic materials, right? Thinking about how you can reduce your plastic use, like the polystyrene lids in coffee cups, right? The black dye that inhibits the recycling so much, and it's purely a cosmetic thing, right? There's no purpose to having that in there other than it looks a little bit prettier, right? We need our materials to be functional, but maybe we should think a little bit more on what the downstream effects of that are. So it's a really challenging problem. I'm excited to do our part on this side and develop the chemistry. But yeah, it's going to take all of us. It's going to take all of society to try and overcome this. Yeah.
So you had like 3 different kind of tacks in your research, and which do you think is likely to kind of make the biggest difference or be the most commercially viable and change the way we recycle plastic?
Yeah, I mean, I think our last strategy of making the cyclic plastics economy is really exciting to us because you can convert it back into virgin materials. In the terms of the second story where we talked about the photooxidative degradation, right? If we can generate value from that material, and so phenol, for example, is a $22 billion industry. Right now, it comes from fossil fuels. So it comes from something called the cumene process, and cumene is only made from fossil fuels to generate phenol. So if we can now turn polystyrene into phenol, that's actually pretty transformative. It's only one of the polymers we use, but there are other groups who are working on polyethylene depolymerization. And so they can convert polyethylene into propylene, which then makes polypropylene. And so I think there is a lot of potential in chemical upcycling or converting these polymers into either monomers or other useful commodity chemicals. Our first work, we're really excited about those copolymerization strategies. I think that one, I think we can make some really interesting niche materials, which are going to be inherently more recyclable or at least reusable. But I guess what I think about every day is how much plastic we're generating, polyethylene, polypropylene, polystyrene every single year, and it's going to take a long time to change that. And so I think we really need to focus in and dig on those materials. And so I think that the oxidative degradation and the chemical recycling to monomer are really the two that are going to make the most impact. But I'm really excited about developing new polymers too. So.
Did you get a lot of interest from industry partners?
We are starting to. Yep. So we're in talks of getting some funding from an expanded polystyrene foam company in California. They are very, very interested to see what they can do with their polystyrene waste. Yeah, because they can't get rid of it. It's worthless, and no one's accepting it anymore. not to bring Friday down, but there's a lot of hope. We're really excited. We're gonna change the world.
Here, do you have? He wants to end it.
Any other questions from online? Otherwise,
I don't think so. Yeah, thanks so much, Erin.
thanks
Yeah.
for having me
Thanks
out.
Yep, thanks for coming, everyone.
All right,
Sounds great.
great. Thank
Okay.
you, everybody.
Good night.